year 10s. Do you remember what we did last week? Do you remember?
There was a word problem which was related to rainfall and filling up of a lake.
That's right. Do you remember what we did last week?
Yes, we have lakes and stuff.
Great. So today we're going to continue from that lesson and connect what we did in our previous lesson and build on that. All right? So if
Just scroll through.
yes, please. Okay. So yeah. So do you remember that statement? Taylor, would you like to sit and face the board?
Page, yeah.
Sorry, page. Yeah? I'm going to give you 30 seconds to a minute to read that. Paul, are you able to see the board? Are you okay there?
Yes.
Yeah, great. All right. Has everyone read that? So now we're going to show you a video, and I want you to keep this statement at the background while you're watching that video. Alrighty?
It's one of Australia's most spectacular sights, the rare greening of our red central deserts. It's a miracle of nature, and nothing short of a miracle that in this thirsty country, these rivers are still largely free to run their course.
We as Australians need to really appreciate what we have in the way of natural heritage.
The Lake Eyre Basin is one of the largest dryland river systems on the planet. It covers 1/6 of Australia across 4 states and territories and is fed by 3 major river systems, the Georgina, Diamantina and Cooper. The shining jewel, more than 1,000 kilometres downstream, is the vast, usually dry salt pans of Lake Eyre, also known by its indigenous name, Cutty-Tunda. Unlike the Murray-Darling Basin, this system is not regulated. There's no major irrigation, diversions or dams, no water security. But the region's 60,000 residents fight to keep it that way, and 730 took a trip through the basin to find out why. William Creek is a tiny, bustling tourist hub 60 kilometres from Lake Eyre. It's pretty much owned and run by Trevor Wright.
It's a multi-skilled business.
Okay, so you've had a glimpse of that. Now I want you to think, as we watch the next 1 minute, I want you to see your idea. Do you pick anything that you can relate to our real world problem? Is that right?
Where you start off doing tyre repairs, you're the publican of the hotel, you're in charge of the water supply, and I'm really passionate about people coming out and
Over the lake and up through the basin.
Oh, it's incredible, isn't it? You look at the patch, the colours, and then you start to see the...
Can you please pay attention to the area? I want you to look at the steepness. Think about how the water is spread out, okay, when you're watching the video.
Bird light come on top of it again, and actually you have the whole system regenerate itself. Totally fascinating.
It's been years since Trevor has seen so much water here. This is one of the world's most variable river systems, so protecting flows when they come is paramount.
How important is it?
All right. So how did you find the video? Maybe you're trying to say something?
I'm not quite sure how it links in just yet. I saw, yeah, it
Okay.
showed the lake a little bit and the river systems.
Okay. So if we go back to a real world problem, are you able to make a connection connection between what you just watched and when the reporter was saying that this lake has been just filled, and when the 7:30 reporter went and had a word with them? Were you able to make a connection?
I'd make a connection with drought probably.
Drought, yeah. And does that help you link the drought with our statement that it does dry up very quickly?
Yeah.
Does it? Can Shan, would you like to explore that idea more?
Sorry.
Did you notice the part where, if you go back, if you see these areas, do you think that will affect the amount of water that a lake holds?
Yes.
Would you like to build on that thought? Explore that thought? Let's explore that thought together. So for example, if you put water in a flowering pot, what happens to the water? So it kind of dissipates, right? Yeah? Yes, there is what?
I was going to say that I've even experienced something similar like this in Mawson Lakes during our summer when it was very dry and barely any rain. It was so dry because it's not just like a bowl, they got like heaps, they got
Right.
bumps.
Yeah.
And so some areas have water.
Sorry, Derek, I'm going to go a bit offline there. So what I'm trying to relate this, sorry, not myself, but what I'm trying to get you to do is relate this to our real world problem. So what I need you to do is, first of all, can you use mathematics in this? If you were to calculate the rate, like how much water, how long will it take? How long? What is long? What is how long? What does how long mean?
Time.
Great. And if we look at this, if you go back to a real world problem directly, sorry, Dylan. Take that out. So if we go back here, how rapidly will the lake empty? What are we looking at?
The time that
Time, but time in what? Is it hours, minutes, days, years,
Months.
months? Ankita?
Few weeks to few months.
Few weeks to few months? Paul, what do you think?
it's 2 months,
Few months? Why do you say few months?
because like everything's like
Exactly. Months. Because it's seasonal. What happens is it fills and then it dries out. Okay? But to be able to solve this problem, do you think you need a calculator?
Not yet because I do not have any numbers.
Exactly. That's right. We don't have any numbers here. So how do we get to the numbers?
you measure stuff.
Exactly. So what do you think using a model in class will help us to solve this problem?
Maybe.
Use to scale.
Maybe if we could just make a model, use scales to compare it to the real, lake, and then we can come to some time period.
So for example, if I gave you a cylinder, like we had one in the morning, a Pyrex cylinder, a beaker, and I did the same thing, and I said, let's put this small beaker outside in the sun and see how quickly the water evaporates. Can we do that?
Yeah.
But would it be a good demonstration for it? Because the lake is big enough and the water would probably evaporate quickly there. And however, in a beaker, it would not give us the exact.
That's right. Ankita, you're drawing up a very good point. But are you able to simulate the same scenario
Yeah.
and take the same scenario from the beaker and apply it to the lake?
Yeah.
Is it right? So what would be, if I had a beaker, what will I be giving you? What would you know if you saw the beaker? Exactly. Well done. Can we see how we are coming to that concept of volume? Can you see that page?
Yeah.
Can we see that, Pushpika? Okay. Do you see how you can bring those two concepts together? So now, can you start putting numbers? Are you able to apply the numbers in this problem?
Yeah, if we get the beaker.
You look lost, Shan. Oh, where you lost? Okay, so if I put a beaker here, you would know the volume, right? But do we know the volume of the lake? So what is that? Assumed. Exactly. We're going to assume that because it remains constant. It's a surface area. It's a 3D object which the amount you put in there is not going to change. Does that make sense? Girls?
How can we say that it is not going to change?
Yeah.
It's definitely going to change.
The maximum amount is not going to change. Does that make sense?
But it will, because then it will just tip over, like there's not a cap on it.
Yeah, because
So, like-
it can only hold that amount. That's the maximum volume that it can hold. Does that make sense?
Overspill doesn't count towards volume when it comes to lakes and rivers.
But then there's a very good point that you bring there. You know why? Because we're leading to seepage. Does that make sense? Gentlemen at the back there, are we together? Yeah? Thomas, what were we discussing now?
Discussing how we're going to work out the answer to the question through volume and assuming that there's amount of water going to be in there.
And were you able to link how we brought in the seepage concept to this? What we brought in seepage? Because one of the questions that was asked was the overspill of the beaker we had.
Like if you put water into
Yeah.
ground, and it goes into the river. That's
Yeah.
So you don't know where the light is.
Exactly. To be on here, ladies at the back there, there's a very good point that was raised. That how do we know the volume of the lake? That I will be providing to you. Okay? So what I'm going to do, I'm going to give you 5 minutes. 5 is too much. 3 minutes. Discuss among what you group. What will be the constants? Constants will be the volume, the surface area, right? Constants will be the Paul, if you could help me with this. The volume remain constant. Volume formulas remain constant for the objects that we're working on. Is that right?
There's no evaporation.
No, it wouldn't. It wouldn't, definitely. Okay. So I want to take this time based on what we have discussed and come up with lists of what assumptions you can make and what information you need to build on. Does that make sense? Alright, away you go. Okay. If I, are you, does this exercise make sense to you?
Yes, it does a little bit that we are trying to calculate the time in which a lake would get dried out.
So you have a volume of, you have the,
It's saying it's a seasonal lake, so it's only doing it once the rainy season is there, and then it goes. So what we need is actually, I think
we
we
don't know
need
the
is the
volume of the
rate
lake, right?
of
We need
rain,
volume of the lake.
and I need the volume of the lake. And to calculate the volume, I need the surface area.
Right?
And then as it goes down, the
She
evaporation.
said she would do it.
So that's
Volume
coming.
will be giving it rest.
Yeah.
Amount of, you know, like, amount of water, which is the volume of the lake, which is the same. Okay? And then you need to think about seepage.
Water going into the ground.
Okay?
We're
So I wanted to discuss that.
absorption.
Like imagine if you had a small beaker that you place outside. If you can relate it, forget about the big lake, just think about the small beaker, right? And we had dry, does that make sense?
So what do we need to actually do? What are we actually trying out? We
So
need
you
to
need
find
to-
out time. So we need to calculate what do we need and what are we going to get. Do you
So
want
if you
us to
have,
do that?
if you have the volume of a beaker, that will mean you know the formula of calculating the volume of the beaker. Yeah,
No,
that's
you don't actually
So
need
then
to
we
do
can
that.
find the rate of evaporation.
right. We need the rate of evaporation.
We cannot
So that
calculate.
becomes rate of evaporation remains fixed.
So usually it's not very
So that's an assumption.
Exactly.
Not fine.
Okay, that's another assumption because it's fixed. So it cannot change, right? So that is something. See, now this is how you're thinking because you need a rate of evaporation which is constant in this case, right? So this is what I'm trying to get you to think. What is it that you need to be able to solve this problem?
So we had this thing, what we do.
Exactly. Does that make sense?
So we know the operation rate.
Now that's what you need to write down. That you need to know what is the evaporation rate. Okay, so write these things down.
We've identified a constant, questionable in itself.
Yes. Yeah, that's what I'm actually looking for because I want you to.
So it's actually what I think is we should work out right what do we need to know
To solve
get
this
to
problem.
solve this problem. What are the things that we need to know related to maths?
That makes sense.
Yeah.
This is a maths
What
exam.
level you basing
Variables we need to know.
I think we need the rate of evaporation. What are the mathematical things?
Exactly.
You are asking me the answer?
Variables as.
Or you are asking me the question?
Rate, evaporation rate, temperature.
We are writing the factors that we need to know to solve this question.
Okay. Do you think we can do this as constants?
This is another
I think
question.
that you already know so area.
Surface area of the lake.
Previously straight.
Rate of evaporation, surface area of the lake.
That's
And the
okay.
depth of
That's
the
not
lake, if it is a square constant depth.
Yeah, so surface area would definitely get to know the depth. Because if we need the volume,
Yeah, you multiply
Yeah,
the
that's
depth and surface
and we
area.
need to know the rate of seepage.
Is it only seepage or evaporation? Both.
Both,
Ways.
because evaporation is
Going
going up
up
and
and
seepage is
then
going down. So
seepage
both of the things we need to know.
Seepage and
That's
the-
it. I think we need to know.
At least of constants. Because what I've seen.
Surface area, that's
Class, class, may I have your attention please? There are some, okay, can we come back together as a class and see what we have got from everyone? Okay, so we can work together and read our thoughts, okay? Thomas, could you please tell me what you came up with there?
Well, the constants that we had was it's a bit questionable, but the volume of the lake and the area, and the variables that we talked about were absorption, evaporation, temperature, erosion, outflow and inflow. And yeah, that's all that we came up with.
Okay, were we able to hear what was said?
I think
In the middle two.
Really good points were mentioned there. So I want you to take this from this lesson, and I will be sending you as a class on Google Classroom the constants that we have, okay? And if you have some time, just put in a little bit, maybe 10 minutes of your time, and go through the constants that I'll be providing to you, okay? The classroom code is OX6F, okay? So this was I really enjoyed this lesson, and I'll see you next week then.